Let's review what we've learned so far in the chapter about the relationship between female legislators, religious attendance on the one hand, and female legislators and college education on the other hand. The female legislators' religious attendance regression revealed a statistically significant negative relationship. The percentage of female legislators declined by 0.535 of a percentage point on average for every 1 percentage point increase in religious attendance. The female legislator college or more regression revealed a significantly positive relationship. The percentage of female legislators increased by 0.878 of a percentage point on average for every 1 percentage point increase in college graduates. A researcher who performed these analyses to test two separate hypotheses, let's call one the religiosity hypothesis and the other the college hypothesis, might be tempted to conclude that each coefficient taken by itself, that is, minus 0.535 for religiosity and plus 0.878 for college degrees, captures the true effect of each variable on the dependent variable. However, this conclusion would be unwarranted. Why? Recall this result, revealed in the correlation analysis that we opened the chapter with. The two independent variables are themselves rather strongly related. You may recall the correlation between the two was minus 0.519. Here's the problem. When we compare states having lower percentages of college graduates with states having higher percentages of college graduates, as we did with the simple bivariate regression, we are also comparing states having more highly religious residents with states having fewer highly religious residents. Here's the question then. Do states with more college graduates have higher percentages of female legislators because they have more college graduates or because they have lower religiosity? How much of the college effect is attributable to the religiosity effect, since the two variables are quite strongly related? Multiple regression analysis is designed to disentangle the confounding effects of two or more independent variables, as in this example. Multiple regression will estimate the effect of each independent variable on the dependent variable, controlling for the effects of all other independent variables in the model. We will perform such an analysis, again using WIM-Leg 2015 as the dependent and entering both BA or more and 10% as independent variables. Let's do that. I'll go to Analyze, Regression, Linear. The BA or more independent variables already in there. Let's click a 10% in. Now we're going to run the regression with both independent variables predicting the dependent variable. I'll go to variables removed so we can see more plainly. Take out the ANOVA table and let's see what we have. Focus on the regression coefficients for each of the independent variables. The coefficient on BA or more, 0.449, tells us the effect of BA or more on the dependent variable, and this is the important part, controlling for the effect of a 10%. Recall that in the bivariate analysis performed earlier, a 1 percentage point increase in BA or more was associated with a 0.878 unit increase in the percentage of female legislators. When we control for religious attendance, however, we find a reduction in this effect to a 0.449 unit increase in the percentage of female legislators. So when we take out the covariance with the other, we control for the covariance of the other independent variable, the pure effect, the partial effect, is reduced. Even so, the regression coefficient on BA or more with a t-statistic of 2.743 and a p-value of 0.009 remains statistically significant on its own. The partial effect of a 10% tells a similar story. The uncontrolled effect of religious attendance, if you recall, was minus 0.535, and that also weakens to minus 0.417, but again remains significant with a t-ratio of 5.042 and a p-value of 0.000. So we can reject the null hypothesis in the case of both independent variables. In multiple regression, adjusted R-square communicates how well all of the independent variables explain the dependent variable. So by knowing two things about states, the percentage of college graduates and the level of religious attendance, we can account for about 56.1% of the variation across states in the percentage of female legislators. This is an improvement over the explanatory leverage of a 10%, which you may recall was 0.502, or BA or more, which was 0.338. Considered separately, we didn't do as well explaining female legislators as we do when we consider both variables together.